Hello everyone and welcome back. My name is Mr. Kovault, and in this video I'm going to be going over how to find the empirical formula of a given substance when you know what type of reactions the elements of that substance undergo. So let's get into this. So you may have heard of combustion analysis, where you take a certain substance and you burn it in the presence of oxygen and it forms certain products. And then from the masses of those products that you get, you can then determine the mass and moles of the elements that came from your original sample. So in that case, when you're doing combustion analysis, as the name implies, the reactions that you're undergoing are combustion reactions. You're burning stuff, right? So the idea, again, is to take the amounts of the products you formed. You know that the elements in the products, or the key elements that are in the products, came from your compound that you burned. So if you know what elements that were in your compound, you can then use the products you formed to convert the masses of those products to moles of the elements that are in the products but also came from your original sample. Okay. And then from there, once you get moles, it's all downhill to find the empirical formula. But you don't have to do combustion analysis to do that. You can do other types of reactions to do the exact same thing. So for this problem, you're doing the exact same thing as combustion analysis, but you're just using different reactions. So let's get into this. Okay, so you have a student. The student takes an unknown sample mass of a compound, and we know that it has Ti and Cl, titanium and chlorine, and they put it in some water, right? So they put it in water, and what happens? They tell us that the titanium formed TiO2, which is titanium 4 oxide, which was removed, dried, and they found the mass of it to be 0.777 grams. Now we have the titanium taken care of through that process. And then what do they do? What about the chloride ion that's in solution? Well, the chloride ion is then picked up when you put the silver nitrate. So silver nitrate was added to the solution. The silver nitrate is going to react, or the silver ions are going to react with the chloride ions, and that's going to convert it to silver chloride, and you get 5.575 grams of silver chloride. So they want you to determine the empirical formula of the unknown compound that has titanium and chlorine in it, or titanium and chloride ions. Okay, so we know that there's titanium and chloride ions in the substance. We just don't know what the ratio of the atoms are in the compound, but they give us the masses of the product. So here we just do the same thing we normally would with combustion analysis. Is we're going to take the masses of the products and convert that to moles of the uh, of the elements that we're interested in. So let's go ahead and start with titanium. So we're given 0.777 grams of TiO2, or titanium 4 oxide. And we want to convert that to moles of just the titanium, because we know in this case all of the titanium in the TiO2 came from our original sample. So if we could figure out what the number of moles are that in this sample, we can figure out that's the number of moles that came from our sample that we're trying to find the empirical formula of. So what do? We need the molar mass to convert this to moles. So when we look up the molar mass, we get 79.865. So 79.865 grams of the titanium 4 oxide on the bottom, and 1 mole of the titanium 4 oxide on top. So grams are going to cancel out. Next, we want to find the number of moles of titanium, and here we can use the mole ratio. So we know that for every mole of titanium oxide, it's going to be 1 mole of titanium. So we can do the mole ratio there. Give me 1 second. Okay, so then that's going to be 1 mole of titanium 4 oxide on the bottom. So 1 mole TiO2 on the bottom, and 1 mole of titanium on the top. So 1 mole of titanium O2 cancels out. And now we can convert this to mass of titanium here. And so we're going to figure out the mass. So we got to use the molar mass of titanium. We looked that up on our periodic table. And we get, let's see here. Actually, we don't need that. We just need moles. So we don't want to go too far. So this is going to be enough. We just need the moles of the titanium. And so when I calculate this out, I get, what did I get? 0.0097289. 0.009, was it 97289? 97289. So 97289 moles of titanium. And then we do the exact same thing with the silver chloride. All of the chlorine in the silver chloride came from our original sample. So when I convert this to from grams of silver chloride, I can get the moles of chlorine from my original sample because all of it is in the silver chloride. So I'm going to take the 5.575 grams of silver chloride, and then I'm going to convert it to moles using the molar mass. And the molar mass of silver chloride is 143.32, I believe. Yep, 32 grams of silver chloride, and 1 mole of silver chloride on the top. So grams of silver chloride cancel out. Now I have moles. And again, the mole ratio of silver chloride to silver is 1 to 1. So we're going to use our conversion. So 1 mole of silver chloride on the bottom, and on the top 1 mole of, not silver. We're not interested in silver. We're interested into the chlorine. So it's going to be Cl minus. So moles of the silver chloride cancel out. And so that's going to be equal to, and when we calculate that out, it's going to be 0.038898. So 0.038898. Let me double check that. 0.038898. And that's moles of chlorine. So now that I have the moles, remember the empirical formula is the lowest whole number ratio between the elements. It's the formula that has the simplest whole number ratio between the elements in the formula. Since we only have two elements here, what you're going to do is set up a pseudo formula to begin with. So we're going to take these moles and we're going to write them as subscripts because that's where the mole ratio is. They're in the subscripts. So since I have moles here, we can write that as subscripts. So I'm going to have Ti, and then as a subscript 0.0097289. And then for chlorine, it'll be 0.038898. Now, you don't need all of these digits. I'm just being ridiculous here a little bit. So you could keep 3 or 4 digits. You just don't want to round too much because you want to get a whole number ratio or a nice number that's going to work out. If you round, you might not get that nice number. So now that I have this written as subscripts, these are obviously ugly subscripts. You don't have these type of subscripts in your empirical formula because in your empirical formula it's supposed to be 1 to something or the smallest whole number ratio. So in order to get a 1 to get 1 to something, you got to divide by the smallest number. So this one's smaller than this one. So if I divide this by this one, I'll get 1, right? And if I divide this by the smallest number, I'll get a number greater than 1, right? That's why you want to divide by the smallest number. So it's going to be 0.009728. Divide this by 0.009728. Obviously, this is going to be 1, so I'm going to end up with Ti 1. And then I divide these. If I divide those, what do I get? I get a number really close to 4. And so you basically get like 3.99819. So you get a number really close to 4. So basically, it's going to be Cl4. And so this is the compound formula. So Ti without the 1, TiCl4 is the empirical formula for this substance. And that, ladies and gentlemen, is how you attack these sorts of problems for finding the empirical formula of different substances. It doesn't have to be through combustion reactions. It's whatever reactions they give you, as long as you know that whatever amount of compound or amount of product is formed, that the elements that are from your original sample are completely contained in the products that you're forming. If that is the case, then you can just take the amount of product and convert it to amount of the elements in the original substance. Once you get moles of the elements in the original substances, you set up your pseudo formula with the actual numbers of the moles that you calculate, and then just divide by the smallest one to get your ratio. And so in this case, we got 1 to 4. It's not always a nice whole number the first time after you divide. You might get something like a half. In that case, you would multiply both of the or all of the subscripts by a multiple to get rid of the half. So if it was a half, you'd multiply your subscripts by 2 to get the whole numbers that you're looking for. But we didn't have to do that here because when we divided by the smallest one, it worked out so that it was a 1 to 4 ratio right off the bat. So that's it for this video. I hope you enjoyed this video. If you did, please like, share, subscribe, hit the notification bell. When you do, make sure you click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a topic you would like me to cover, if you have a particular problem or question you need help with, put that down below. I would love to help you with that. Thanks for joining me and have a great day.